All right, let's dive right in. Today, we're going to create a kind of blueprint for bone health by taking a close look at the drugs used to treat osteoporosis. But, to really get how these medications work, we've got to start with the incredible, dynamic world that's constantly happening inside our own skeleton.
So let me start by asking you a question. Think about it for a second. Are the bones in your body right now the exact same bones you had a decade ago? I think most of us kind of picture our skeleton as this permanent, solid frame that doesn't really change, but is that actually true?
Well, the answer is a pretty surprising not at all. Seriously, far from being this static, unchanging thing, your skeleton is one of the busiest construction sites in your entire body. It's in a constant state of demolition and reconstruction every single day of your life. So let's get into it. Let's explore this ever-changing skeleton of ours. We're going to dive into the amazing process that keeps our bones strong, and we'll see what happens when that system gets a little off balance. This whole constant activity has a name. It's called bone remodeling, and it's exactly what it sounds like, a lifelong process where old, worn-out bone is systematically broken down and replaced with fresh, new bone. Just think of it like a never-ending renovation project that makes sure your skeleton can handle all the daily stresses and repair any tiny bits of damage. So how does this work? Well, every construction site needs two essential crews, right? You need a demolition crew and a building crew. In our bones, it's the same deal. The demo crew are cells called osteoclasts. Their job is to break down or resorb old bone. And the building crew? Those are the osteoblasts, and they form all the new bone. The whole goal for a healthy skeleton is to keep a perfect balance between these two crews. Okay, so how does this whole project actually play out day to day? Let's walk through the beautifully coordinated step-by-step cycle of bone remodeling to see exactly how these crews work together. It all starts in a resting phase where the bone surface is just kind of chillin'. Then some kind of signal kicks off the activation phase, waking up the cells that will become our crews. This brings in the osteoclasts, our demo crew, for what's called resorption, where they get to work clearing out the old bone. After they're done, the site gets prepped for the builders in the reversal phase. Then, in the formation phase, the osteoblasts show up to lay down a soft protein matrix. And finally, that new matrix hardens up with calcium and phosphate. That's mineralization. And boom, you've got strong new bone. Then it's right back to the resting phase until the next cycle begins. Now, a project this complicated can't just run itself, right? It needs a manager, it needs signals to keep everything in balance. So let's take a look at the key molecules that control our demolition and building crews.
Okay, so the main go signal for the demolition crew is a protein called RANK-L. When certain cells release RANK-L, it's basically like the foreman yelling, "All right, time to get to work." It tells the osteoclasts to mature and start breaking down bone.
But you can't just have demolition going wild all the time. That would be a disaster. So the body has this really clever safety switch, a protein called OPG. OPG basically acts as a decoy. It floats around and grabs onto the RANK-L signal before it can reach the osteoclasts, telling the demo crew, "Nope, stand down for now." That delicate balance between the go signal RANK-L and the stop signal OPG is absolutely crucial. And at the very same time, there's a whole system to control the builders too. A protein called sclerostin acts as a brake on the osteoblasts. It blocks a key pathway they need to function, which slows down bone formation. So you can see, our body is constantly managing both sides of this equation, hitting the gas and the brakes on both demolition and construction. And all of this finally brings us to osteoporosis. So what is it? Well, in terms of our construction site, osteoporosis is simply what happens when that balance is totally lost. The demolition crew, the osteoclasts, starts working way faster and harder than the building crew, the osteoblasts. When you've got more bone being broken down than is being built, the skeleton gets weak, porous, and much more likely to fracture. Okay, so now that we understand the problem, we can finally talk about the solutions. The first major strategy for treating osteoporosis is all about putting the brakes on that overactive demolition crew. These drugs are called the anti-resorptives. So let's start with RANKL inhibitors, like the drug denosumab. This is where the science gets really cool. This drug is basically engineered to act just like OPG, the body's natural stop signal. It's a lab-made protein designed to hunt down one specific target, in this case, the go signal RANKL. By binding to and neutralizing that signal, it stops the osteoclasts from ever getting the message to start work. The result? A whole lot less demolition. Next up, we have the bisphosphonates. And these use this amazing Trojan horse strategy. It's really clever. The drug itself is designed to stick to bone minerals, so it just sits there on the bone surface. Then, when the osteoclasts come along to do their demolition job, they end up absorbing the drug right along with the bone. And once it's inside, the drug shuts down a key enzyme the osteoclast needs to live, essentially disabling it from within. It's a brilliant way to specifically target that overactive demo crew. So putting on the brakes is one strategy, but what about the other side of the problem? Well, the second major approach is all about boosting the builders. We use drugs that actually stimulate the osteoblasts to build more bone. These are called the anabolic drugs. Now, this is where things get really interesting, because parathyroid hormone, or PTH, is kind of like a double agent. See, at high constant levels, it actually increases bone breakdown. But, and this is the key insight, if you give it in low, intermittent doses, like with drugs such as teriparatide, it does the exact opposite. It powerfully stimulates the osteoblasts, leading to some serious bone growth. It all comes down to how that signal is delivered.
Okay, to understand the next class of drugs, let's just quickly revisit the building cruise control system. Remember that protein, sclerostin? It's the natural brake that blocks the pathway telling osteoblasts to build new bone. Now, this is a normal part of how our body works, but with osteoporosis, we really want to find a way to take that brake off. And the solution? A class of drugs called sclerostin inhibitors. Medications like romosozumab are another one of these highly specific lab-made antibodies. They're designed to do one thing: find and bind to the sclerostin protein. By taking sclerostin out of the picture, this drug effectively releases the brake on the building crew, unleashing the full bone-forming potential of our osteoblasts.
Okay, so let's pull all of this together now and take a look at our complete blueprint for managing bone health. This table sums it up perfectly. You've basically got two core strategies. You have drugs that put on the brakes by targeting the demolition process, like bisphosphonates going after the osteoclasts directly, or rankle inhibitors blocking their activation signal. Then, on the other side, you have drugs that boost the builders, like PTH analogs and sclerostin inhibitors, which directly tell our osteoblasts to get to work and build more bone. So, by understanding this really intricate dance of demolition and construction happening in our bones, we've developed some incredibly powerful tools to step in when that balance is lost. We can pretty effectively tell our bones when to stop and when to go, which really just leaves us with one final thought. Now that we have this amazing level of control, what's the next frontier in skeletal engineering?